Welcome to the deep dive, where we sift through the noise, extract the most crucial insights from a stack of information, and give you the fast track to being truly well informed. Today, we're diving into something that on the surface feels invisible, yet it impacts almost every piece of technology you interact with daily. Think about it. Tangible objects over time wear down, right? Your
Mhm.
car rusts, your house settles, clothes fray. Obvious stuff. But what about software? It's intangible, just lines of code existing in digital space. Yet it's absolutely no exception to the relentless forces of decay. We call it software rot, and it's this insidious process where a once clean, elegant code base gradually becomes rigid, fragile, and incredibly difficult to change. It's not just a risk. Without a disciplined, principled approach to design, it's an absolute inevitability.
That's precisely it. It's like imagining a perfectly organized library, everything in its place. But over years, maybe through neglect, books get thrown everywhere, pages are torn, shelves start collapsing. It's just chaos because no one maintained the structure.
Okay.
That's essentially what happens to software. As new features are bolted on, bugs get hastily fixed, requirements twist and turn.
Hmm.
These small compromises, they just accumulate.
You build up, right?
Exactly. They form this truly tangled web
Mhm.
of interconnections. And that makes the system incredibly slow to respond to new demands. It gets enormously costly to modify, and frankly, it's profoundly demoralizing for the development teams.
Yeah.
The people who have to wrestle with it day in and day out. This silent degradation, it directly impacts their ability to innovate and deliver value back to the business.
And that's where today's deep dive comes in. We're introducing you to the strategic antidote to this digital entropy, the solid principles. Think of solid not as some rigid, dogmatic rulebook you have to follow blindly, but more like a foundational philosophy, a strategic framework. It's for creating what we call soft software systems, and by soft, we mean incredibly pliable, adaptable, and resilient. This framework is your shortcut, really, to building applications that remain understandable, flexible, and maintainable. Not just for today's deadline, mind you, but for years down the line, gracefully accepting change rather than fighting it tooth and nail.
Absolutely. At its heart, Solid is all about mastering the art of managing dependencies and organizing your code effectively. It provides a robust blueprint for constructing systems that can evolve, absorb change, and continue to deliver value without collapsing under their own complexity and weight. We're about to set the stage for you, giving you a clear, concise understanding of these crucial principles. Hopefully, we can illuminate those aha moments you need to truly grasp how and why these principles are so vital for software longevity and, ultimately, business agility.
Okay, let's unpack this then. Our mission for this deep dive is to distill the five solid principles down to their absolute essence. We'll help you understand the individual power of each one, and perhaps even more importantly, truly see how they work together, like precision gears in a finely tuned machine, how they combine to create truly robust and adaptable software. We're going to explore their fascinating history, dive into practical, real-world examples that bring them vividly to life, and then we'll discuss when and how to apply them pragmatically in your own work, ensuring you're designing with purpose, not just blindly following some checklist.
And it's crucial to remember, this isn't merely about technical rules, not just for the sake of code purity. These principles are a strategic investment in the future. They are about building systems that can adapt to constantly changing business needs, respond quickly to shifts in the market, and continuously deliver measurable value. Understanding them means understanding how to build software that actively serves the business's goals, rather than becoming a perpetual hindrance, or worse, a source of escalating technical debt.
Let's dig deeper into this idea of software rot, because it's more than just a vague, abstract concept you might hear muttered by, seasoned developers. What does it actually look like when it manifests in a software system? You might hear developers lamenting about rigidity or fragility. Rigidity is when even a seemingly simple, isolated change, say, altering a user interface element or tweaking a discount calculation somehow cascades. It just creates this massive ripple effect, requiring modifications across dozens of files or modules that you'd never logically expect to touch. It's like trying to adjust a single light bulb in a poorly wired house, and suddenly half the block goes dark.
Precisely. And fragility. That's when a change in one seemingly isolated part of the system unexpectedly breaks functionality in completely unrelated distant parts of the application. It's akin to pulling a thread on one side of a tightly woven but ultimately fragile sweater and watching the whole thing unravel on the other side. Nightmare stuff. This isn't just a nuisance. It's a fundamental and pervasive challenge in long-term software development. The relentless management of complexity. When a project begins, the architecture might be pristine and simple. You have a clear vision, well-defined modules, maybe a shiny new framework. Looks great.
Yeah, the honeymoon phase.
Right. But then new requirements roll in. A critical bug needs a quick patch, or a new feature gets rushed out with an aggressive deadline. Each one of these instances, if not handled with disciplined design, introduces new, often unseen dependencies. These dependencies aren't immediately obvious, but over months and years, these small compromises accumulate. They weave themselves into that tangled web we talked about earlier. It makes the entire system incredibly difficult to reason about, to debug, and to predict. Developers literally become afraid to touch anything.
Because they don't know what might break.
Exactly. They don't know what might break or how far the breakage might extend. This makes development agonizingly slow, incredibly costly due to constant bug fixing and rework. And ultimately, it's profoundly demoralizing for the engineering teams who are forced to work within such a brittle, unpredictable structure. The solid principles were developed specifically to combat these very symptoms of software rot by systematically reducing those unwanted, unpredictable dependencies.
So, given how critical these principles are for avoiding such pain, where did these foundational ideas actually come from? Who's behind the strategic framework that has become so ubiquitous in modern software development?
Well, the core principles that eventually formed the SOLID acronym were introduced by a renowned American computer scientist, Robert C. Martin. He's widely known throughout the industry as Uncle Bob. He published a pivotal paper back in 2000 called Design Principles and Design Patterns.
Uncle Bob, a legend in the field.
Absolutely. He's a really significant figure, particularly within the agile software development and software craftsmanship movements. He essentially distilled these concepts from his extensive hands-on experience building and maintaining highly complex, long-lived systems. He codified patterns that, many senior engineers implicitly knew but hadn't really formally articulated in this way.
Okay, so Uncle Bob laid the groundwork.
He did. But while he laid the intellectual groundwork for the individual principles, it was actually another influential voice in the software community, Michael Feathers, who coined the memorable SOLID mnemonic acronym. That was around 2004. He grouped these 5 principles together to make them easier to remember, discuss, and teach.
Ah, so Feathers gave it the catchy name.
Right. And it's important to note their origin in the Agile community. This isn't just a historical footnote. It's profoundly significant, because these principles were specifically designed to enable the very adaptability, responsiveness, and continuous delivery that Agile methodologies champion. Agile without SOLID often just evolves into rapid, uncontrolled accumulation of technical debt. It gets messy fast. SOLID provides the structural integrity that allows Agile teams to actually be Agile long-term by making change cheaper and safer.
Okay, that makes sense. So at the absolute heart of the SOLID philosophy are 2 fundamental concepts. You mentioned them briefly. They sound technical, maybe a bit abstract at first, but you say they're quite intuitive once you grasp them. Coupling and cohesion.
Let's break those down, because understanding them is really the key to understanding SOLID. Coupling essentially measures the degree of interdependence between different software modules like classes or functions. Think of it like a chain. If every link is tightly welded to the next, that's tight coupling.
Bad news.
Very bad news. A change to one link immediately impacts all the others. And if one breaks, the whole chain might fail catastrophically. This is a primary cause of software rot because changes ripple unpredictably through the system, creating that fragile mess we talked about. SOLID aims to achieve loose coupling. That's where modules are as independent as possible. They interact only through stable, well-defined interconnectors. Picture Lego bricks. They snap together cleanly, but you can also easily separate and replace them without breaking the whole structure.
Okay, loose coupling. Got it.
Yeah.
Legos.
Right. This allows you to work on one part without constant fear of affecting another. Then there's cohesion. This measures how closely the elements within a single module are related to each other. High cohesion means that all the methods and properties inside a class, for example, work together to achieve one single, well-defined purpose. It's a focused specialist class.
Doing one job well.
Exactly.
Yeah.
On the flip side, low cohesion is when you have what we often call God objects or bloated classes. These are classes that try to do too many unrelated things, like a single chef trying to also be the accountant, marketing manager, and delivery driver for a restaurant. It's just too much. They become incredibly difficult to understand, test, and maintain because they're juggling too many disparate responsibilities. Essentially, SOLID is a set of 5 distinct strategies, each contributing in its own unique way to achieve this architectural goal of consistently low coupling and high cohesion across your code base.
So, to put it simply, for you, the developer listening, what this boils down to is building organized, resilient code bases. Code that's ideally a pleasure to work with, easy to understand, and capable of evolving gracefully over time.
And beyond the direct technical improvements to the code structure itself, the formalization of these solid principles provided something equally, if not more, valuable.
Huh.
It gave us a shared vocabulary for software development teams.
Ah, common language.
Precisely. Before Solid became widely adopted, discussions about design could be quite abstract, subjective, and prone to misinterpretation. One developer might say, "This class feels a bit messy," which isn't very actionable, is it? But now, when a developer states in a code review, "This class is violating SRP because it handles both business logic and data formatting," it's not a vague opinion. It's a precise technical critique grounded in a shared understanding of what constitutes good design. This common framework profoundly improves communication across the team. It accelerates the onboarding process for new developers because they can quickly grasp the foundational design philosophy that underpins the codebase. And perhaps most importantly, it aligns the entire team's mental model of what a well-architected system looks like. That significantly reduces friction, ambiguity, and ultimately design debt in the collaborative process of building and maintaining software. It ensures everyone is speaking the same architectural language.
Now for the core of our deep dive. The 5 pillars that make up Solid. Each one is a tactical advantage on its own, a powerful guideline for specific design decisions. But together, when you combine them, they become incredibly powerful, creating a truly robust and adaptable system. We're going to break down each one, give you a memorable analogy to help it stick.
Analogies are key for this stuff.
Definitely. And then show you exactly how it applies in code with examples of what to avoid and how to do it right. Let's kick off with the S in Solid, the Single Responsibility Principle, or SRP. Now, instinctively, you might think it's more efficient to just pile all related user functions like authentication, saving to a database, sending emails into one big user or user manager class, right? Seems simpler, maybe. A single file to manage everything for a user. But this principle, arguably the most foundational, flips that thinking on its head. It states, a class should have one, and only one, reason to change. Why is that seemingly counterintuitive idea so revolutionary?
It's revolutionary because it forces us to think about change. That's the crucial part. The well-run bakery analogy is perfect for this. In such a bakery, you have different specialists, right? The baker's job is to bake bread. If the recipe changes, only the baker needs to know and adjust. Simple. The inventory manager is solely responsible for ordering flour and sugar. If a new supplier is chosen, only they are affected, and the cashier handles sales. If the point-of-sale system updates, only the cashier needs retraining. Each person has a single, clear responsibility.
Makes sense. Specialization.
Exactly. Now imagine a single person trying to do all three. Bake, manage inventory, and handle sales. Chaos. If recipe changes, they also have to remember how it impacts inventory and sales. Then the sales system updates, adding another layer of complexity. It would be inefficient, highly prone to errors because one change impacts multiple unrelated concerns. A class trying to do all three would be exactly that, chaotic and fragile. Where a change in one area risks disrupting all others, it becomes a maintenance nightmare.
Okay, let's look at a concrete example of what not to do. A common violation of SRP that you might see in real-world code bases, perhaps even ones you've worked on. Our source shows a user managing class. Let's say it's written in JavaScript or Java, doesn't matter too much. This single class is tasked with handling user authentication, saving user details to a database, and sending a welcome email. So internally, you have this user manager with methods like authenticate, username, password, save user to database, user object, and send welcome email, user email, all bundled together.
And here's the stark violation. This user manager class actually has 3 distinct, independent reasons to change, not just one. Consider the scenarios. First, the authentication logic might need updates. Maybe your security team decides to add 2-factor authentication, or you change your password hashing algorithm, or integrate with a new single sign-on provider. That's one reason.
Right, security changes constantly.
Exactly. Second, the underlying database technology could change entirely. You might migrate from a relational database like SQL to a NoSQL solution, or maybe switch your object relational mapper, the tool mapping objects to tables. That's a completely separate reason to change the class.
Okay, data storage changes.
And third, the content, formatting, or even the delivery method of that welcome email could change. Your marketing team might decide to rebrand, or you might switch from one email service provider to another. Yet another independent reason. Each of these independent changes forces you to modify this single user manager class. This tight coupling of unrelated responsibilities makes the class incredibly difficult to maintain. You're constantly poking at this one large multi-purpose object. It also makes it challenging to test. To unit test the authentication logic, you'd have to mock out or deal with the database and email sending dependencies, making tests slower and more complex than they need to be.
So we've identified the problem, that tangled user manager. And I bet a lot of our listeners are now wondering, all right, how do we actually do this? How do we fix it? Walk us through applying SRP effectively.
The fix is elegant in its simplicity and relies on the principle of decomposition, basically breaking it down. We refactor by separating each distinct responsibility into its own focus class. So instead of one user manager, you'd create first a user authenticator class dedicated solely to authentication logic. Think authenticate, hash password. Its only reason to change is changes to authentication rules.
Okay, one class for auth.
Second, a user repository class, responsible only for database interactions, saving, retrieving, updating users. Its reason to change is changes to data persistence mechanisms, your database stuff.
Right, data layers separate.
And third, an email service class. Its only job is to format and send emails. Its reason to change is changes to email content, formatting, or the underlying delivery service. Now, each class has a single, well-defined purpose. A change to your email template only requires modifying email service. A switch in database technology only affects user repository. This design is dramatically more robust and organized because changes are isolated, minimizing that blast radius we talked about.
And the benefits must be pretty clear then.
Oh, absolutely. The benefits are substantial and immediate. First, improve maintainability. By isolating responsibilities, changes to one part are far less likely to cause unintended side effects elsewhere. The code becomes more predictable, easier to understand, less fragile. Second, enhanced testability. Writing focused unit tests for a small, single-purpose class is significantly simpler, faster, and more reliable than for a large, monolithic one. Each can be tested in isolation. Better tests, higher quality. And third, better organization and readability. A code base made of small, well-named classes with clear responsibilities is just inherently easier for developers to navigate, understand, and reason about. It clarifies the architecture, makes onboarding new team members much smoother.
Okay, that makes a lot of sense. But is there a risk of taking it too far?
Ah, yes. The common misconception with SRP, a frequent pitfall is interpreting single responsibility as one method per class, or even one line per class. That's not it. This can lead to hyper-decomposition, where logic gets fragmented into an excessive number of tiny classes. It actually obscures the overall workflow. The key is reason to change, not simply counting lines or methods. If a class has multiple methods but they all serve the same single concern and would change for the same reason, then SRP is likely still being upheld. It's about finding the right balance.
Okay, from ensuring our classes have a single purpose with SRP, we now shift our focus. How do we design our code so it can easily grow and adapt without us having to constantly rewrite existing stable functionality? That's the essence of the open-close principle, or OCP. The O in solid. This principle states that software entities should be open for extension, but closed for modification. Meaning, once a piece of code, a class, a module, whatever is developed and thoroughly tested, you should be able to add new functionality without having to go back and change that existing, stable, proven code. Because any modification to existing working code always carries that risk of introducing new bugs, right? OCP aims to minimize that risk, fostering stability.
Exactly. And the smartphone analogy is absolutely perfect for understanding OCP because it's something everyone uses daily. Think about your phone's operating system, iOS or Android. The core OS is effectively closed for modification by you, the user. You can't just go in and rewrite the fundamental code.
Right, Apple or Google wouldn't like that.
Not at all. But the phone is brilliantly open for extension because you can add tons of new functionality simply by installing apps from an app store. You extend the phone's capabilities, adding games, productivity tools, social media, all without ever touching or modifying its stable, tested core operating system. The original OS developers don't have to push out an update every single time a new app is created. That's the power of OCP in action. Stable core, extensible periphery.
Okay, that's a great analogy. So where does this go wrong in code? What's a common violation?
A common violation happens surprisingly often, particularly in code bases that grow organically without strong architectural guidance. It occurs when you see code relying on large switch statements or long if-else chains to handle different types or behaviors. Let's imagine an area calculator class. Its job is to calculate the area of different geometric shapes. In a design that violates OCP, this class might have a calculate area method that looks something like this. If shape.type will calculate circle area, else if shape.type, use in square. You see this pattern a lot.
Ugh, the big if else block. Yeah, I've seen those.
And the violation here is glaring. If you or another developer want to add a new shape, say a triangle or an ellipse, you are forced to go into that existing area calculator file and modify it directly. You have to add another else if block. This directly violates the OCP because you are changing existing, potentially well-tested code. Every time you modify it, you risk introducing new bugs into a part of the system that should otherwise be stable and reliable. This approach makes the system brittle, inflexible, and incredibly difficult to scale with new requirements because the core logic is constantly being reopened for modification. You're constantly patching rather than extending.
So how do we make it adaptable? How do we design this area calculator so it can accommodate new shapes without ever being touched again? Truly embrace that closed for modification, open for extension ideal.
The solution lies in using abstraction and polymorphism. This is a core OOO concept. Instead of the area calculator directly knowing about circle or square, we introduce a shape abstraction. This is typically defined as an interface or an abstract base class. This shape abstraction declares a method, let's say area. Then, circle, square, and our new triangle each implement this shape interface. And they define their own specific area method containing the logic relevant only to their particular geometry.
So the logic lives with the shape itself?
Precisely. The area calculator then becomes incredibly simple. It just takes a collection of shape objects and iterates through them, calling shape.area on each one. The beauty is the area calculator doesn't know or care about the specific concrete type of shape it's dealing with. Is it a circle? A square? Doesn't matter. It just trusts that any shape object will correctly implement its own area method.
Okay, so adding a new shape is easy then.
Trivial. To extend the system later and add, say, a triangle shape, you simply create a new triangle class that implements the shape interface and provides its own area calculation. You don't touch the area calculator class at all. It remains closed. This perfectly demonstrates that the system is open for extension. You can add new shapes by creating new classes, but closed for modification. The area calculator remains unchanged, stable, and reliable. This is a foundational pattern for building plugin architectures.
And the benefits of doing it this way?
Significant benefits. First, stability and reduced risk. New bugs are far less likely to be introduced into stable, well-tested code because new features are added in isolated new classes, less messing with working code. Second, enhanced flexibility and scalability. The system becomes highly adaptable to changing requirements. New features can be plugged in with minimal effort, promoting a truly scalable and modular architecture, crucial for long-lived systems where requirements are guaranteed to evolve. And finally, improved maintainability. Code that follows OCP is easier to maintain because new functionality is self-contained and doesn't complicate existing logic or introduce unforeseen side effects. You're designing for change rather than just reacting to it.
Are there pitfalls here too, like with SRP?
Oh yes. A frequent pitfall with OCP is premature generalization. Developers sometimes try to predict every possible future extension and build elaborate abstraction layers for features that may never actually change. They over-engineer the flexibility. This violates the you ain't gonna need it principle, or YAG&I. It adds unnecessary complexity and maintenance overhead for hypothetical future scenarios. The trick is to apply OCP when you identify a likely point of variation or when a new variant actually emerges, rather than trying to build a perfectly extensible system for everything from day one. Often, you refactor to OCP, you don't always start with it.
Now for the L, the Liskov Substitution Principle, or LSP, named after the pioneering computer scientist Barbara Liskov. This one can sometimes be a bit tricky to get your head around, but it is absolutely crucial for building robust, reliable, object-oriented systems, especially when you're dealing with inheritance. It states that subtypes must be substitutable for their base types without altering the correctness of the program. What that really boils down to, as I understand it, is that a child class, a subclass, must be able to seamlessly replace its parent class anywhere in the code, without causing any unexpected behavior, errors, or breaking assumptions in the program. It has to honor the contract the parent implies, not just in its methods, but in its behavior. Is that about right?
That's exactly right. It's all about honoring the behavioral contract. And the rectangle square problem is the most famous and illustrative example of an LSP violation. It really highlights this behavioral contract issue. Mathematically, a square is a rectangle, right? Length and width are just equal. So instinctively, you might think a square class could inherit from a rectangle class. Makes sense on the surface.
Seems logical.
But this creates a fundamental behavioral problem when you consider how objects are used. A rectangle object typically has independent width and height properties. A client using a rectangle object expects to be able to set its width without affecting its height and vice versa. That's the implicit contract. Now, if you substitute a square object into that client code and you set its width, a square must also set its height to maintain its squareness.
Ah, the side effect.
Precisely. This hidden side effect, where setting one dimension also sets the other, breaks the expectation of a client code that was designed to work with a general rectangle. This leads to unexpected results and clearly violates LSP because the square is not a behavioral subtype of rectangle in this context, even if it is taxonomically. Another classic example often debated is the bird class with a fly method. A sparrow inheriting from bird and implementing fly is fine, makes sense.
Yeah.
But what if you have a penguin subclass? Penguins are birds, but they definitively cannot fly.
Right, penguins waddle, they don't fly.
Exactly. So if penguin inherits from bird and its fly, method simply throws an exception or does nothing. It breaks the behavioral contract. A client expecting any bird object to be able to fly will either encounter an error or unexpected behavior when given a penguin. The penguin is not a valid substitute for a bird in the context of flying. It violates the expectation.
So these examples highlight that subtle but critical distinction between is a in classification and can be substituted for in terms of behavior. How do we uphold this crucial behavioral contract? How do we ensure our subclasses behave as expected and prevent these kinds of subtle, hard-to-debug problems?
Adhering to LSP often requires a fundamental rethinking of how we design inheritance hierarchies. It's not always the right tool. Inheritance should strictly model a true behavioral is a relationship, not just a taxonomic or data relationship. In the rectangle square case, a square does not behave like a general rectangle when it comes to setting independent dimensions, so inheritance is often inappropriate there. A better design might involve avoiding inheritance entirely for these two, or maybe having a more abstract geometric shape hierarchy that both rectangle and square can implement independently without forcing square to inherit from rectangle. The key is that operations on the base type should not lead to unexpected or incorrect results when a subtype is used. The behavior must be consistent.
And for the bird example, how do you handle the penguin?
For the bird example, the correct approach to uphold LSP is often to segregate behaviors using interfaces. This ties into the next principle, ISP actually. Instead of a single bird class with a fly, method that all birds must implement, even if it means throwing an error for non-flying birds like penguins, we could do something different. We could have a base bird interface that defines common bird behaviors like eat and lay eggs. Then we introduce a separate capability interface, maybe called flyable, with just a fly method. Now, a sparrow class would implement both bird and flyable. Makes sense. Crucially, a penguin class would only implement bird because it cannot fly. It doesn't get the flyable interface.
Ah, so the client code asks for what it needs.
Exactly. Client code that wants to make a bird fly would then only operate on objects that implement the flyable interface. This ensures that any object passed into a function expecting a flyable creature will in fact be able to fly, preventing runtime errors and upholding LSP. It's about ensuring type safety behaviorally, not just structurally based on inheritance.
And the payoff for getting LSP right.
The benefits derived from LSP are substantial. First, reliability and predictability. It ensures your class hierarchies are behaviorally sound, preventing those subtle, nasty bugs from incorrect substitutions. Your code becomes more robust because you can trust that objects will behave as expected. Second, enables true polymorphism. LSP is really the foundation that makes polymorphism reliable and powerful. It allows high-level modules to safely operate on base class references, confident that all subtypes will behave correctly according to the defined contract, critical for flexible systems. And finally, improved code reusability and modularity. It fosters the creation of reliable and interchangeable components, essential for building modular, maintainable, and truly robust software systems. You can swap out implementations with confidence.
Okay, moving on to the iron solid, the interface segregation principle, or ISP. This one states, clients should not be forced to depend upon interfaces that they do not use. The core idea here, as I understand it, is to prefer many small, specific interfaces, often called role interfaces, over one single, large, general-purpose interface, sometimes called a fat interface. Think lean, focused interfaces for focused clients. It's about precision in the contracts we define.
That's spot on. And a great analogy here is the restaurant menu again. If a customer is strictly vegetarian, they should ideally be given a vegetarian menu containing only relevant options. Forcing them to sift through a huge comprehensive menu with relevant meat, seafood, dozens of desserts. It just makes their experience cumbersome and inefficient, unnecessary noise and clutter.
Right, just give me what I need.
Exactly. Or consider a multi-function printer, those big office machines. They might have an interface defining methods for print, scan, and fax. Yeah. Now, if you then have a simple single-purpose desktop printer that can only print, but it implements that big interface, it would be forced to implement empty or maybe error-throwing methods for scan and fax simply because the interface demands it. This forces the client, the simple printer, to depend on and implement irrelevant methods. It pollutes its responsibilities and creates unnecessary coupling to things it doesn't do.
So that fat interface sounds like the common violation of ISP. The source gives a classic example, an iWorker interface that includes both the work method and an eat method. Then a robot worker class is created. Because it implements iWorker, it's forced to provide an implementation for eat, even if that implementation just throws an unsupported operation exception or does nothing because, well, robots don't usually eat lunch.
It's exactly right. The violation is that the robot worker is polluted with an irrelevant method, eat, which it has no business implementing. This creates an unnecessary dependency on a method completely unrelated to its core purpose, working. And it forces a potentially awkward or erroneous implementation. What should eat do for a robot? Log an error, silently fail. It also makes the code less clear and potentially misleading. A method exists for something that simply isn't a true capability of the object. Worse, if you had to change the eat method signature later, maybe add a parameter like eat food type, the robot worker would be forced to change too for no good reason. This is exactly the type of unwanted ripple effect ISP aims to prevent.
Okay, makes sense. So how do we fix this? How do we make interfaces lean and clean, aligning with ISP, ensuring our robot worker doesn't have to pretend to eat?
The solution is pretty straightforward. Segregate the fat iWorker interface into smaller, more cohesive role interfaces. Break it down. We would create an iWorkable interface with just the work method, and a separate iEatable interface with just the eat method. Now, a human worker can implement both iWorkable and iEatable because humans can generally both work and eat.
Makes sense. Humans do both.
Right. However, a robot worker would only implement iWorkable since that's its sole relevant capability. It doesn't need iEatable. Crucially, client code, like maybe a manager class that assigns tasks, can now depend only on the specific interface it needs. If the manager's job is simply to tell workers to work, it can declare its dependency on iWorkable. This means the manager class isn't exposed to or dependent on the eat method, which is completely irrelevant to its task of managing work. This granular dependency reduces complexity and improves focus for both the implementing classes, like robot worker, and the client classes, like manager.
And the benefits here seem pretty clear, too. Less baggage for everyone.
Quite impactful benefits, yes. First, decoupling and reduced dependencies. Clients only depend on the methods directly relevant to their needs. This dramatically reduces coupling. If a change occurs to the iEatable interface, for example adding a digest method, it only affects classes that actually eat, not those that only work. Less ripple effect. Second, improved cohesion and readability. Smaller interfaces with a clear single purpose are significantly easier to understand, implement, and maintain. This also leads to higher cohesion within the interfaces themselves, making the system's contracts very clear. And finally, greater flexibility. ISP allows for more precise and flexible class implementations. Classes can pick and choose precisely which role interfaces to implement based on their actual capabilities, rather than being forced into a large, generic, often irrelevant contract.
Is there a danger of going too far here as well, creating too many tiny interfaces?
Yes, absolutely. That's the common pitfall with ISP, creating too many interfaces, especially for very simple classes or single method scenarios, where the interface only serves to wrap one simple function. While ISP advocates for small interfaces, creating an interface for every single class or method can lead to interface proliferation. It makes the code base harder to navigate, increases cognitive load due to excessive indirection, just more files to manage. The key is to segregate interfaces only when a client truly doesn't need all the methods defined in a larger interface, or when different clients require different subsets of functionality. Don't create an interface just for the sake of it. Create it to manage dependencies and avoid forcing irrelevant contracts onto clients. Use judgment.
Finally, we arrive at D, the Dependency Inversion Principle, or DIP. This is arguably the cornerstone of building truly decoupled and flexible architectures, and it really flips how you typically think about dependencies on its head. It has two parts, which often get bundled together. First, high-level modules should not depend on low-level modules. Both should depend on abstractions. And second, abstractions should not depend on details. Details should depend on abstractions. It sounds a bit like a tongue twister and abstract in itself, but it's incredibly powerful once you grasp its core meaning, right?
It does sound complex initially, but the TV remote and batteries analogy simplifies it perfectly.
Right.
It makes it very intuitive. Think about your TV remote. That's your high-level module. It dictates the policy, change channels, adjust volume. Does it depend on a specific brand of battery, like Duracell or Energizer? Those would be the low-level concrete details.
No, thankfully. That would be annoying.
Exactly. If it did, you'd need a different remote for every battery brand. Instead, the remote depends on an abstraction, the AA battery standard. Any battery manufacturer at the low-level detail creates batteries that conform to this AA standard, the abstraction. This is the inversion of dependency. The remote doesn't depend directly on the specific battery brand. Instead, both the remote and the battery brands depend on that agreed-upon AA battery standard. The policy, or mode's function, is decoupled from the mechanism, the specific battery brand. This is also why dependency injection, DI, is the most common and practical way to implement DIP. DI is the mechanism through which you provide those abstract dependencies, like the battery standard, to your high-level modules, the remote at runtime, rather than letting the high-level module create them itself.
Okay, the remote and battery standard makes sense. Let's look at a typical violation of DIP in code, a scenario you might frequently encounter. Imagine a notification service. This is your high-level module responsible for the business logic of sending out various types of notifications, maybe user-registered, order-shipped, things like that. In a DIP violation, this notification service might directly create and depend on a concrete email client. That's your low-level module handling the specifics of actually sending an email. So the notification service constructor might explicitly say something like this, .email client equals new email client, tightly binding itself to that specific implementation.
And the violation here is clear. The high-level notification service is rigidly and tightly coupled to a specific low-level implementation detail of the email client. This design is inherently inflexible and brittle. If, down the line, the business decides to switch from email notifications to SMS notifications, or maybe add push notifications, the notification service class must be modified directly. You have to go in and change its core logic just because an underlying implementation detail changed. That's exactly what we want to avoid.
Right, the business logic shouldn't care how the message gets sent.
Precisely. It prevents the system from being truly adaptable because the high-level policy, sending a notification, is directly dependent on low-level concrete mechanisms, sending via this specific email client. If the email client itself changes its constructor or its own dependencies, the notification service is impacted too. It's fragile.
So how do we achieve true flexibility here? How do we make our notification service able to send messages through any channel, email, SMS, push without ever being modified itself? How do we invert that dependency?
To adhere to DIP, we introduce an iMessage client abstraction. This would typically be an interface in most OO languages. Both our email client and a new Spence client, and maybe a push notification client, would then implement this iMessage client interface. Each provides its own specific send message method implementation. Now, the notification service is no longer responsible for creating its dependency. It doesn't say new email client. Instead, it declares that it needs an iMessage client, and this iMessage client is injected into it. The most common way is through its constructor.
Ah, so it asks for the capability, not the specific class.
Exactly. So your notification service constructor would take client, iMessage client. It just expects something that knows how to send messages. Now, when you create an instance of notification service somewhere else in your application, maybe using a DI framework, you can provide it an email client or an ENS client or any future client that implements iMessage client. The notification service itself remains completely unchanged. You can swap from email to SMS simply by injecting a different object at runtime without changing a single line of code within the notification service itself. The high-level module remains stable and focused on what to notify, not how it's notified. This is incredibly powerful. It's a cornerstone of robust, maintainable systems. This is often managed by specialized frameworks or inversion of control, IOC containers in larger applications. They handle the creation and wiring up of these concrete implementations at runtime, further simplifying your high-level code and making it incredibly adaptable.
The benefits here sound pretty immense. Decoupling seems to be the major theme.
Immense benefits, yes. First and foremost, loose coupling. DIP dramatically reduces the coupling between high-level business logic and low-level implementation details. Creates an incredibly modular and flexible system where components can be swapped out easily. Second, enhanced reusability and testability. High-level modules become highly reusable with various low-level implementations. And for testing, it's remarkably easy. You just inject mock or stub objects for dependencies, like a mock email sender that just logs calls instead of sending real emails. This allows units to be tested in complete isolation from external systems like databases or actual web services. Dramatically speeds up testing, increases reliability, and finally, improved maintainability. The system is far easier to maintain because implementation details can be changed or swapped out entirely without affecting the core business logic. For example, your entire data access layer could be replaced, moved from SQL Server to Postgres without needing a single modification to the high-level services that use it, as long as the new layer implements the same data abstraction interface, like our repository.
Okay, powerful stuff. Any common mistakes people make when trying to apply DIP?
Yes, a common mistake is conflating DIP with just using dependency injection. While DI is the primary mechanism to achieve DIP, they are not the same thing. You can use DI without strictly adhering to DIP if you inject concrete classes rather than abstractions. You might be injecting, but you're still coupled to the concrete type. DIP's core insight is the direction of dependency. Both high-level and low-level modules should depend on abstractions, inverting that traditional flow. Another pitfall is over-inversion, creating interfaces for every single class by default, even for stable ones unlikely to change. This adds unnecessary layers of indirection for no practical gain. DIP should be applied strategically, where concrete implementations are likely to vary, or where a stable interface is needed for testability and flexibility. Don't just interface everything blindly.
We've unpacked each principle individually now, and you can see how powerful they are on their own. Each one has a specific design pattern to apply. But you mentioned earlier their true magic happens when they're applied together synergistically, like a symphony orchestra.
Exactly. Where each instrument plays its part, but the collective sound is what really matters.
Right. And it's not just about cleaner code, though that's a huge benefit. You said it's profoundly about business strategy and the long-term health and adaptability of an organization.
That's a crucial point, and it's where the deep dive into solid truly pays off. When solid principles are applied cohesively, the most immediate and tangible benefit you observe is significantly enhanced maintainability and a substantial reduction in technical debt. By rigorously enforcing the separation of concerns through principles like SRP and ISP, and by deeply decoupling modules, especially with DIP, Solid dramatically reduces what we call the blast radius of any given change. When a modification becomes necessary, fixing a bug, adding a feature, updating a library, developers can work on a small, isolated component with confidence. They know their changes are far less likely to cause that cascade of unforeseen failures across the entire system. This isolation makes the codebase inherently easier to understand, simpler to debug, and safer to modify. You spend less time chasing elusive bugs introduced by unrelated changes.
So what does this all mean for you, the listener, and for a business? It directly translates to less technical debt. Think of technical debt as those unseen interest payments on shortcuts taken in the code, or on designs that implicitly sacrifice long-term flexibility for short-term speed. Tightly coupled, low cohesion code is technical debt. It's the silent killer of productivity, accumulating in the background until suddenly simple tasks take exponentially longer. Solid, by contrast, builds code that is designed to be changed. This architectural resilience means developers spend significantly less time untangling complex dependencies, fixing ripple effect bugs, or trying to understand obscure spaghetti code. Instead, they spend more time delivering new features and real value, which directly and significantly lowers the total cost of ownership for the software over its entire lifecycle. It's an upfront investment that pays dividends for years.
And beyond maintainability, a solid architecture delivers superior scalability and flexibility. This is because it is fundamentally built for change and for growth. The open-closed principle, OCP, and the dependency inversion principle, DIP, are particularly crucial here. OCP champions adding new functionality as extensions rather than modifications. This means the system can grow in capability without destabilizing its existing, tested core. For instance, imagine a large-scale e-commerce payment processing system. If it's designed with OCP, adding support for a new payment method like a regional digital wallet, crypto, buy now, pay later simply involves adding a new module that implements an existing payment interface. You don't need to rewrite the central payment logic handling existing credit cards or PayPal. That's true horizontal scalability for features.
That seems incredibly valuable for staying competitive.
Hugely valuable.
Yeah.
Similarly, DIP provides the flexibility to swap out low-level implementation details without touching high-level business logic. Consider a major enterprise system communicating with various data stores. If it depends on an IDA store interface rather than directly on a concrete SQL Server repository, you can migrate the entire database technology, say, from SQL Server to PostgreSQL, or even to NoSQL like MongoDB, with minimal disruption to your core business logic. Just provide a new implementation of iData Store. This level of architectural flexibility isn't just a technical nicety, it's a powerful competitive advantage. It empowers an organization to adapt rapidly to new technologies, pivot quickly to evolving market demands, and avoid being locked into expensive, high-risk, system-wide rewrites every few years. Your tech becomes an asset, not a liability.
This truly isn't just a technical nicety or a developer's preference. It's a profound competitive advantage for any organization that relies on its software to function, grow, and respond to market shifts. It's about building a future-proof foundation.
And then there's robust testability. Solid principles naturally cultivate code bases that are incredibly easy to test. This is a massive factor in both speed of delivery and software quality. Effective unit testing absolutely relies on the ability to test components in isolation. Solid's inherent emphasis on decoupling makes this straightforward. DIP is particularly key here. Using dependency injection, developers can effortlessly substitute mock or stub implementations of dependencies during testing. For example, that notification service depending on email sender. Test it with a mock email sender that doesn't actually connect to a network or send real emails. The mock just verifies the send method was called correctly. This allows incredibly fast, reliable, automated testing of your business logic without needing external systems or real-world costs.
Faster feedback loops for developers.
Much faster. Furthermore, SRP significantly contributes by ensuring each class has a narrow focus. This simplifies writing comprehensive test cases for each class, fewer paths and states to cover. Simpler tests are faster, more reliable, easier to understand. The net result? A system with much higher test coverage, which invariably leads to greater code quality, significantly fewer bugs in production, and massively increased confidence in the software's overall reliability. Happier developers, happier users.
Which means more confident deployments for development teams and ultimately a better, more reliable, and more secure product for you, the end user, with fewer unexpected crashes or bugs.
And finally, let's not forget developer productivity and team collaboration. A clean, consistent, well-organized code base, the direct outcome of applying Solid, has a profound positive impact here too. When responsibilities are clear and modules are decoupled, it becomes vastly easier for multiple developers or even entire teams to work in parallel on different parts of the system with minimal interference. This dramatically reduces frustrating merge conflicts, complex integration issues, and the need for constant laborious communication about internal module changes. It streamlines the whole workflow. Think smooth-flowing lanes on a highway versus a traffic jam.
It also significantly reduces the cognitive load for individual developers, right? Easier to jump in.
Yeah, exactly. The code is more readable, the system is designed more predictable. That allows new team members to become productive much faster. They don't spend weeks untangling spaghetti code. This accelerated onboarding reduces project delays, lowers the cost of knowledge transfer, and improves communication through that shared vocabulary we discussed. Everyone's on the same page about how the system is designed. So, if we connect this to the bigger picture, all these technical benefits, maintainability, scalability, testability, they aren't ends in themselves. They are the essential mechanisms that enable greater business agility. In today's rapidly evolving competitive landscape, the ability of an organization to respond quickly to new market opportunities, pivot based on customer feedback, and continuously innovate is paramount. A software system burdened by high technical debt and tight coupling acts like a heavy anchor. It makes every new feature slow, expensive, and risky to deploy. Each minor change can require extensive regression testing. The constant fear of breaking something stifles true innovation. Organizations miss opportunities.
Okay, let's distill that down. In stark contrast, a solid architecture directly fuels agility. When a system is inherently easy to change because components are isolated and interfaces are clear, the organization can iterate faster on new ideas. When new features can be added as modular extensions without destabilizing the core, the business can pivot quickly to meet new demands with confidence. And when the code base is highly testable, deployments can happen much more frequently and reliably, allowing for continuous delivery of value and rapid experimentation. It's the difference between trying to steer a supertanker and a nimble speedboat.
Therefore, the extra effort, or perceived upfront cost, often associated with diligently implementing Solid, shouldn't be viewed as a mere development cost or a technical luxury. Instead, it should be reframed as a strategic investment in the company's operational capability. By fundamentally reducing the friction of change within the software itself, Solid principles directly enhance an organization's capacity to innovate, adapt, and deliver sustained value to its customers in a timely, reliable, and cost-effective manner. It's about building software that empowers the business, not hinders it.
Okay, the theory of solid is compelling, undeniably powerful. The benefits are clear on paper, but applying it in the real world, that's where the true art of engineering comes in, doesn't it? It's about pragmatism, wisdom, judgment,
Mhm.
not blind dogmatic adherence to rules. There's a vital balance to strike, and often that balance is learned through experience, through trial and error.
You've hit on the most frequent and potent criticism leveled against solid: the perils of dogma. A blind mechanical application of these principles without a deep understanding of their spirit or the specific problem they're meant to solve very often leads to over-engineering. When developers apply the letter of the law without truly understanding the why, the underlying trade-offs, the goals of the resulting code base can paradoxically become more complex, more abstract, even harder to understand than the one it replaced. This phenomenon is sometimes described as producing code that, while technically decoupled and testable, is ultimately unintelligible, academic, or what some might even call a solid mess. The cure can become worse than the disease if you're not careful.
A solid mess. Okay. Can you give specific examples of these pitfalls?
Sure. One is hyper-decomposition in the name of SRP. In a zealous attempt to ensure every class has only one responsibility, developers can break down logic into an excessive number of tiny fragmented classes. While each individual class might be simple in isolation, understanding a single business feature might then require you to navigate dozens of files, jumping from one tiny class to another. It actually obscures the overall workflow and increases cognitive load. For instance, you probably don't need a full class solely to format a date string or set a simple page title. Those concerns might be perfectly fine within a slightly larger but still cohesive entity. The goal is maintainability, not atomization.
Right. Don't make it harder to follow the flow.
Another common pitfall is over-inversion when applying DIP. This happens when developers misinterpret DIP as meaning every concrete class must have an interface. They start creating interfaces for every single class by default, even for low-level components that are stable, unlikely to change, or have no real alternative implementations. This adds an unnecessary layer of indirection, more files, more boilerplate code, and increased cognitive overhead for absolutely no practical gain. It makes the code harder to read, harder to reason about, adds complexity without delivering flexibility, violating the KISS principle. Keep it simple.
Okay. Interfaces everywhere isn't always the answer.
Not always. And then there's premature generalization when trying to apply OCP. This is building complex extension points and layers of abstraction, perhaps a whole plugin architecture for future capabilities that may never actually need to be extended or changed. You're investing significant time and complexity today to solve a problem that doesn't exist yet, which runs contrary to other pragmatic principles like you ain't gonna need it or yayo ain't I. You're paying the complexity cost without reaping the flexibility reward.
The core lesson here seems to be apply solid thoughtfully, with purpose, and with a keen awareness of your specific context, not mechanically. The guiding question should always be, is this design solving a real, present, or highly probable future problem I have? Or am I just creating unnecessary abstractions and indirection for some hypothetical, distant, and perhaps unlikely future scenario? It's a fundamental engineering trade-off.
That's precisely it. Solid isn't a universal panacea, a silver bullet for all design problems. There are absolutely valid reasons to deviate from a strict adherence to its principles, and making that nuanced judgment call is part of the art of software engineering. The decision to apply these principles and to what extent should always be driven by the long-term goals, the expected life cycle, and the unique context of the specific project.
So when might it be okay not to go full solid?
Well, for instance, in short-lived projects and rapid prototypes, code designed to be discarded shortly after user proof of concept, a hackathon project, a quick data migration script. The overhead of meticulously crafting a solid architecture just isn't worth the effort. Speed is the goal, not long-term maintainability. Similarly, in very small, simple projects, maybe single developer applications or internal tools with minimal expected change, the benefits of extreme decoupling might actually be outweighed by the increased complexity of managing numerous interfaces and tiny classes. A more direct, straightforward, even slightly monolithic approach might be perfectly effective and simpler to maintain in that specific context. Simplicity today might trump abstract flexibility tomorrow.
What about performance?
Good point. In performance-critical code embedded systems, real-time apps, high-performance computing, the layers of abstraction and indirection introduced by Solid, particularly DIP, can sometimes have a measurable performance cost. CPU cycles, memory usage. In such highly constrained environments, a more direct, tightly coupled design might be a necessary trade-off to meet stringent performance requirements. You might accept some maintainability costs for raw speed. And critically, when Yaganai, you again need it, prevails. This principle advises against implementing functionality or creating abstractions before they are actually needed. This directly tempers OCP's call for extensibility. It's often far more pragmatic to build the simplest, most direct solution first. Then, if and when the need for extension or flexibility actually becomes a concrete, demonstrated requirement, perhaps that switch statement starts getting huge, then refactor it towards a more solid design. This iterative, just-in-time approach is often far more effective than prematurely complicating your code base based on speculation.
What's fascinating here is that even though Solid was born from the world of object-oriented programming, its core ideas about managing dependencies and organizing code have proven remarkably durable, universally applicable, almost. They seem to transcend specific programming paradigms and are foundational to other styles and architectures, too.
Indeed, they really do. Take functional programming, for example. The spirit of Solid translates beautifully. The single responsibility principle maps directly to the ideal of small, pure functions. Functions that do one thing and do it well, producing predictable outputs for given inputs without side effects. Each pure function has one reason to change: its specific calculation or transformation. The dependency inversion principle is mirrored in the common functional practice of using higher-order functions, where behavior, a function, is passed in as an argument, effectively decoupling the calling code from a specific implementation detail. The calling function operates on the abstraction of a function, not a concrete, hard-coded one.
Interesting. And what about microservices? That's huge today.
Absolutely foundational to modern microservice design. The single responsibility principle is the guiding light for defining service boundaries. Each microservice should ideally own a single, well-defined business capability, just as a class should have one reason to change. A user service handles user data. A payment service handles payments, not both. This prevents the microservice equivalent of those God objects. And the dependency inversion principle is reflected in how services communicate. They interact via well-defined technology-agnostic APIs. Those act as the abstractions, like REST, GraphQL, message queues. They don't depend on the internal implementation details or specific technologies of other services. This allows services to evolve independently without breaking clients.
So the core ideas persist across different styles.
They do. You could summarize modern Solid, the spirit that applies broadly, even beyond classic OOP, with some timeless guidelines. Don't surprise readers of your code. Make its behavior predictable. Use sane, well-defined boundaries for your modules. And apply the right level of coupling. Keep things together that truly belong together and change for the same reason, that's high cohesion, and keep them apart if they belong apart, that's loose coupling. It's all about thoughtful separation and predictable interactions.
It's important to remember that Solid doesn't exist in a vacuum. It interacts with other widely accepted principles like KISS, keep it simple, stupid, and DRY, don't repeat yourself. These are all tools in the same toolbox, and understanding their interplay, and sometimes their tension, is key to becoming a truly effective software engineer.
Absolutely. There's often a perceived tension between KISS, keep it simple, stupid, and Solid. A solid solution, with its explicit interfaces, abstract layers, multiple smaller classes, can appear more complex up front than a direct monolithic implementation. However, this is a critical trade-off between short-term simplicity and long-term simplicity. The simple solution today, built quickly without design principles, can very quickly become tomorrow's unmaintainable, rigid, and ultimately complex system due to accumulated technical debt. Good design is about finding the simplest possible solution that works while still respecting the principles that will allow it to be maintained and scaled over time. They aren't mutually exclusive. They act as checks and balances on each other, preventing over-engineering and under-engineering.
And what about DRY versus SRP? Don't repeat yourself versus single responsibility.
Right. DRY is about avoiding the duplication of code. Don't write the same logic twice. SRP, as we discussed, is about avoiding the duplication of reasons to change. These are generally complementary, but they can sometimes conflict in subtle ways. Let me give an example. Imagine two different parts of an application have identical validation logic, say, validating a user profile's email format and validating an order's shipping email format. The code looks the same. A naive application DRY might abstract this identical logic into a single shared email validator function or class. Seems efficient.
Okay, reuse the code.
But if this validation logic serves two fundamentally different business domains, user profiles versus orders, it now potentially violates SRP. Why? Because that single shared email validator now has two distinct reasons to change. If the validation rules for order emails change in the future, for example, maybe allowing specific shipping domain suffixes, but user profile email rules do not change. Modifying that shared validator to accommodate the order change could inadvertently break the user profile validation. Oops. In such a scenario, allowing a small amount of carefully managed code duplication might actually be the correct choice to maintain the single responsibility of each module. It prevents future complex bugs and supports independent evolution.
Exactly. These are tools. They require judgment and purpose to wield them effectively, rather than just blindly swinging them around.
You mentioned earlier how experience shapes the view of solid. Can you elaborate on that engineer's journey? Yeah, the journey of a software engineer's relationship with solid is fascinating. It really reflects their growing experience and maturity. For a junior developer, the principles often appear as a set of rigid, inviolable rules, must follow. This initial phase can, ironically, lead to that kind of over-engineered, unintelligible code we talked about. Interfaces for everything, classes broken down way too much. This literal early application often stems from learning the what of solid, without fully grasping the why, the trade-offs, the real problems being solved, the context.
Learning the rules before the reasons.
Right. Then, as developers gain more experience, they frequently enter a phase of skepticism or even frustration. They start to recognize that dogmatic application can add complexity without clear benefit. They see the unnecessary indirection, the increased file count. They begin to question the universal applicability, especially in fast-moving or small projects. This is actually a critical, healthy stage. It forces critical thinking about when and where to apply these tools. They shift from rules to guidelines.
So skepticism is part of the process.
A vital part. Finally, with deep experience and a mature understanding, senior developers and architects arrive at a nuanced, pragmatic understanding. They no longer see solid as rigid rules, but as a flexible mindset, a powerful toolkit for managing long-term risk and complexity. They learn to apply the principles selectively and strategically, focusing on parts of the system where change is likely or where decoupling provides significant business value. They understand solid is a tool to serve broader business goals, not an end in itself. This mature perspective allows them to wield the principles effectively, creating architectures that are both robust and practical, delivering real value. #tag outro.
We've taken a deep dive today into the solid principles, a foundational philosophy born from decades of software craftsmanship, from the trenches of complex system development. They are, at their core, a strategic framework that helps us build software that's designed to last, actively fighting off that pervasive software rot we talked about at the beginning, ensuring our digital creations remain pliable and resilient.
And to reiterate, solid collectively promotes maintainability, scalability, flexibility, and robustness. It achieves this by systematically guiding developers toward designs characterized by low coupling and high cohesion. This ultimately boosts developer productivity and, most importantly, enables greater business agility. But it's crucial to remember the critical truth we explored extensively. The true value of solid lies in its pragmatic application, not in dogmatic, checklist-driven adherence. Blindly applying these principles without understanding the context or purpose can indeed lead to over-engineering, unnecessary complexity, and even less maintainable code, undermining the very goals they aim for.
So for you, the learner, the developer, the architect listening right now, here's some actionable recommendations. Ways to integrate solid principles into your daily workflow, transforming theory into practical wisdom and elevating your craft.
Okay, first, start small and refactor incrementally. Don't try to overhaul an entire legacy system with solid all at once. That's usually a recipe for burnout and failure. Instead, adopt an iterative approach. Apply these principles rigorously to all new features and modules you develop. That's the easy part. Yeah. For existing problematic legacy code, identify the areas that are most frequently changed, are prone to recurring bugs, or are critical to your business, and begin refactoring those areas first, incrementally. This makes the task manageable, delivers immediate improvements, and allows you to deliver value quickly as you progressively enhance your code base.
Makes sense. Bite-sized chunks.
Second, prioritize readability and simplicity, above all else. While you're striving for solid design, never lose sight of the ultimate goal, creating code that is easy for humans, including your future self, to understand, debug, and modify. If applying a solid principle results in a design that is more confusing, overly abstract, or less intuitive than a simpler alternative, it's highly likely you've applied it incorrectly or in the wrong context. Always favor the simplest solution that effectively meets the requirements and upholds the spirit of the principles. Simplicity is often the highest form of sophistication in engineering.
Simpler is usually better if it works.
Third, leverage tools and foster team practices. Make solid principles a shared responsibility within your team, part of your collective engineering culture. Utilize static code analysis tools, SonarQube, ESLint, whatever fits your stack, which can automatically identify potential violations and provide objective, consistent feedback. Crucially, incorporate discussions about Solid into your regular team practices, like code reviews and pair programming sessions. This helps enforce standards, share knowledge, and mentor less experienced developers in the nuanced art of good design. Builds that feedback loop.
Get the whole team involved.
And finally, think critically, not mechanically. Before you apply any principle, always ask why. Why does this class need an interface here? What specific future change am I really trying to protect this module from? Is this abstraction I'm considering solving a real present problem that causes pain? Or am I building for a purely hypothetical one that might never materialize? This critical thinking is the absolute key to avoiding over-engineering. Ensure every design decision serves a clear, practical purpose that delivers tangible benefits rather than just adding complexity for its own sake.
The solid principles aren't just technical guidelines then. They're truly an investment in the future of your software and, by extension, the future capabilities of your organization. They empower teams and you to build systems that can evolve gracefully over time, meet unknown challenges with confidence, and continuously deliver reliable, high-quality value to a business, rather than becoming a drag on its progress, forcing costly rewrites down the road.
This raises an important question for you, the listener. Considering everything we've discussed today, the insidious pitfalls of software rot, the profound power of these principles, and the absolute importance of pragmatic, context-driven application, what concrete steps will you take, starting today, maybe tomorrow, to ensure your software is not just functional today, but truly prepared for the unknown challenges and opportunities of tomorrow?
So what does this all mean? It means you have the power right now to build software that not only stands the test of time, but actively fuels innovation and propels your projects and your career forward into the future.